Hi everyone, are you able to hear me clearly and see my screen clearly? Let me just check my audio settings once again. All right, all right. So looks okay for me. Great, great. Hi Bintao, hi Kamal, hi Noor. All right, so should we start? Hi Balaji. Great to have you all in the session. All right, so we will continue from where we had left in the SVM, but I just want to give a quick recap of what we had done in the SVM so that we can, because there has been a bit of a gap, so it'll be better to do a quick recap. All right, great, great. So after the SVM, we'll be starting with decision trees, and then we will learn ensembling, and then we will do the principal component analysis and other similar activities, similar topics. All right. All right. So first we started with understanding what is the classification. So we talked about separating the okay, separating uh, the instances with the line, and we realized that the line that was separating either this one or this one or this one, neither of them were perfect, right? And then we talked about that we should try to have a maximum possible margin between them. So instead of this kind of lines, we would, instead of minimizing the distance from the line like this, we should try to fit widest possible street between the two classes. Okay, so that's the main idea behind the linear SVM classification. Okay, all right. So then we talked about that we must scale the data in order to get better results. Afterwards, we talked about so this is what we talked about, that we should scale the data in order to get better results. And okay, then we talked about soft margin versus hard margin. Hard margin was basically we don't tolerate even one instance on the wrong side of the decision boundary, right? So hard margin is not practical, while the soft margin is something that is more practical, right? So, all right. Now, so SVM classification can be done using the SVC algorithm with the kernel as linear, and the street margin could be controlled with C. All right, and so we learned how to plot the data with different margins. So lower the C, bigger is the margin. Lower the C, bigger is the margin. Then, right. So we talked about there were actually three ways of doing the SVM classification. Is one using SVC, other using linear SVC, and third one using HCD classifier. Okay. Now, then we talked about nonlinear SVM classification. So the idea was to add more features as a polynomial, add more features as polynomial features. But the problem with say for example, we have this kind of data where data is inseparable because they are all in the same line. So we add more features to make it separable. Okay, like for example, we square these values, and then the data will be more separable. So this is how it looks. Okay, so the value of one feature remains as such, while the other feature became bigger, and therefore it has separated the two classes. Okay, so that was basically how adding polynomial features can make the data more separable. All right. So then we tried to we basically generated a random data using Moon's dataset, and and then we try to add the polynomial features there. Okay. So this is the kind of data we had, and this is the kind of data we had. Okay. So these are really complex to separate it, right? So what we did was we added more polynomial features. Okay, and then like we talked about adding more polynomial features, and after adding polynomial features, we were able to separate it. Okay, we were able to separate it. Now, okay, now then we talked about something called SVC kernel. Okay, so even though we did not go into the detail, as in how exactly the kernel is implemented, so so how exactly the kernel trick is implemented, but we just talked about how to use it. So, adding polynomial features worked great. The low polynomial degree cannot deal with complex data sets, and therefore high polynomial degree makes it work, but the model becomes slow because there are many features. So in such cases, we use the kernel trick. Okay, so it makes it possible to similar result when using the high polynomial degree. All right, so this is what we this is how we use it, like SVC, and then we pass an argument called kernel equals polynomial, and then we pass the rest of the argument. Okay, so all right, then we talked about one regularization parameter called R. Okay, so if R is higher, it is basically the curve is more round, and so on. So let me just, this coefficient 0 is basically that R. All right, so that was our regularization parameter. Then okay, now the another technique of solving nonlinear classification was add features. N- Not only so in the just now a couple of slides back, what we did was we added the features which were polynomial features. Instead of that, what we do is we add another another features which are basically derived from the existing features, in a way that they compute the similarity as in similarity to other features. So we convert each feature as your what do you say, each feature as the landmark, and then compute the similarity features. So for example, here, if we create the say we have this kind of features which are kind of linearly in the same line. And so what we do is we create another feature which will have curve like this or curve like this. So there will be many features and they'll be easily separable. Okay. All right. So here is an example of the same thing. So if we had data like this, if we had a straight line data and we compute the similarity features, they would come somewhere like this, and that will be easily separable. So using that same linear classification, we can separate them. This is called RBF. Okay, so that's what we talked about. And all right, okay. Now when we add more such features, more similarity features, so what happens is, again, you will have just too many features, and it will kind of become really hard to handle so many features. All right, so this we had talked about. Okay, okay. So first one was that when we add polynomial features, the 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 training became slow as the degrees became higher, in the polynomial degree became higher. So the kernel trick we use there also solves it. Similarly, when we add similarity functions, again, we'll have a lot of features. And again, SVM kernel trick will help you solve such kind of situation. Okay, so, all right. So the kernel basically lets the RBF kernel or simply kernel lets us get similar result as if we had added many features without actually having to add them. Okay, so yes. All right, so we talked about this, and all right. Again, gamma is another hyperparameter. So we talked about gamma in the equation that we had here. Yeah. So gamma was, if you remember, so gamma was, if we increase gamma, the distance will become smaller, right? If we increase gamma, this distance will become smaller. Okay. And if we reduce gamma, then the distance will become higher. Okay. As in the similarity will, sorry, not distance. I think this is similarity only. Okay. Now let's go ahead. Right. So we talked about how increasing gamma actually um, made it round. Okay. And so on. So we talked about different parameters. Okay. So when we increase gamma, it makes bell curve. When we increase gamma from 0.1 to 5 or zero point 0.1 to 5, this is a better example to compare. If we increase from 0.1 to 5, right? So increasing gamma makes bell curve narrower, right? The bell curve became narrow. And it reduces influence of each instance. Okay, so if you increase gamma, the influence of each instance is, okay, it reduces influence of each instance. All right, if you increase gamma, descent boundary becomes irregular. That is clear. So, all right. So, yeah. So basically these three things. So it makes the bell curve narrower, okay, reduces the influence of each instance. Instead, there is, okay, so, but to me, it looks like that it has kind of, um, okay, okay. So all basically these gamma and C both are hyperparameters. Again, we have to do the grid search in order to find the right best possible gamma and C. Okay. All right. A general thumb rule, I think that this is the important part. So while doing the SVM classification, which kernel to use when? Okay. So first of all, we should try the linear SVC. Okay. The linear SVC, which is faster than SVC with the kernel equals linear for larger data set with a lot of features. Okay. And then we should try the RBF kernel, and then we should try the other kernels. Okay. In simple words, we start with linear SVC, then we move on to the RBF kernel, and then how we do that? Using the cross validation and grid search. Okay, so linear SVC is based on lib linear library and scales linearly with the number of instances. Okay, so if you have just too much of training data, and and uh, you, and you want to do the classification, you should choose the linear SVC first. And the time complexity is m into n. We talked about time complexity last time. The SVC class is based on another library called libsvm. Okay, it supports SVC. This one supports the kernel tricks. The time complexity is m square into n, which is higher than the linear SVC. And when the number of instances become m is the number of instances, by the way. So and n is the number of features. So when the number of instances become higher, the complexity will become, as in the time consumed, will become really high. As in, when the number of instances go higher, the time will increase by square. So therefore, it becomes really, really slow as number of instances grow. Okay, and a question from Noor is there a possibility to mix algos, or do we have to separate the population to groups for different algos? Very good question. This is where ensembling comes into picture. So what we do is, in ensembling, we basically use, we sample the data, we pick the like 10 samples, and we pick separate samples for separate algorithms, and then we train the different algorithms there, and we choose the ones which are more, there are multiple strategies there, so we can actually do, uh, generally combining or mixing algorithms give you better result. Okay, mixing algorithms give you better result. Yes, we are going to go into details of ensembling. So there will be 3-4 strategies. We will discuss those strategies in ensembling. And the you remember in the first chapter, we talked about random forests, right? So that was actually, random forest was nothing but um, many more decision trees together. So it's basically an ensembling. So in general, in practical, the performance, in practical, most of the machine learning projects, we use the combination of algorithms, not a single one. Okay, wonderful, wonderful question. Now, all right, here was an overview. So, okay, so linear SVC and SDD classifier both were with time complexity m into n, while the SVC was really slow, m square n to m cube n, which is very slow, which is going to be slow with respect to the m. Okay, and therefore we use the SVC only when we have more features or more complexity in the data. Well, but the number of instances are lower. So that's when we use the SVC. Okay, so this is where we were. Now, the SVM can also be used for this. I think this is till this point we had covered earlier. So linear SVC is fast. SVC is slow for large data set, perfect for small but complex training sets. And SDD classifier, it does not converge as fast as linear SVC does, but can be useful for data set that do not fit into the memory. Okay, so this is where we use the SDD classifier. Great. Now, great. So the SVM regression is basically on the same, based on similar technique as we just discussed. Let's just go over SVM regression a little bit more, and then we will continue with the decision trees. Okay. Now, in SVM classifier, the idea was the way algorithm worked was to find the largest possible street between the two classes. Okay, and we were basically doing the trade-off between limiting the margin violation and the street width. Correct? That's what we were doing in case of SVM classifier. Now, in the SVM regression, we basically fit as many instances as possible on the street while limiting the margin violations. Okay, so here we were trying to have widest empty street possible. Here we are trying to have the most crowded street as possible, right? And so basically we will try to decrease the width of this what do you say, the street, and fit as many instances on it as possible. And we will also while we'll try to fit it, there'll be violations that we have to take care. Okay, so basically the SVM regression is very similar to SVM classifier. Okay, so the width of SVM regression model is controlled by this hyperparameter epsilon. Adding training instances within the margin does not affect the model's predictions. Okay, hence model is set to be epsilon sensitive. Okay, so if we have, let's say we trained our model based on this kind of data, and one more data point comes up for training, let's say here, it would not impact the model at all, right? Because it'll be the same model. And therefore, the model is set to be the epsilon sensitive. Okay. So just like linear SVC, we have linear SVR here, and it's pretty simple to use. let's try to do that. So inside the ML folder, all right. So this is our data generation. All we are doing is, let's say internally we have this model 4 plus 3 into x. We are just adding a bit of noise. All right. So R stands for regression and C stands for classification. Okay. Also, let me first finish this part. Let me just run everything above. Or do we not need it? I think if we need it, we'll just run it again. Okay. So this is one part that we would require. Okay. So question from Noor is, isn't this wrong? Meaning if the model is fixed as shown in the slide, and in future, if more than 50% of the data points are added, which are parallel to the middle line, okay, but they are in the street, okay, then the model won't be changed. However, we will get the wrong precision. Okay, so okay, so the point from Noor is, let's say we have this kind of a model, right? So we add, and this is something that we have come up with. Now, let's say we put more points towards the middle line. Okay, like more 50% of the data are added to the middle line. Okay, and okay, so then the model won't be changed. However, we will do the wrong predictions. Okay, so since it's epsilon sensitive, so we basically, okay, parallel to the middle line. Okay, let's say here, right? Here somewhere, but there it is inside the street itself, right? Inside the margin only. Okay, so let's say, yeah, let's say we have here these data points, and the epsilon that we have chosen is the same one. So we will try to fit the street onto the data points by and we'll try to minimize the violations of the street, right? And since the data points are lying in the same street, we would not um, So the simple idea is that we will keep on decreasing the epsilon to the point where we have so the idea is to find the smallest street having minimum violations, correct? Smallest street having the minimum violation. Now, since the new data points are fitting here, the violations would not be changed, would not be there, would not be changed. They would be as such as they were before, and therefore the model wouldn't change. Now, question is, doesn't that lead to wrong results? The answer is no, because that is the smallest street anyway that would fit with minimum margins. Just that let's say when we are talking about huge number of data sets, huge number of records added, in that case, what will happen is the street might shift a bit so that the margins, so that some of the violations we might increase or decrease because we are fitting a better street. So when we are adding 50% or like significant number of records, then the model would change. So you are right in that sense, that model would change when we have significant amount of data added, right? But when we are adding only few records, in that case the margin violations are not changing and we are not trading off with the margin violation. But in case of significant data, the model would change. So yes. All right. So your hypothesis is right. Okay. All right. Now let's try to, this is the, okay, good. All right, great set of questions. So first of all, a question from Abhinav is that, but then we keep on updating model when large amount of new training data gets added. That's right. Okay, so all right. So this is a simple data that we're trying to generate. It's a standard one, and this is something when testing most of the regression algorithm, this is what we do in general in the beginning. So here, what we're doing is we have generated some values of x, and then we are generating some values of y using 4 plus 3x, and then we are adding some amount of noise, and then we are plotting it. So this is the kind of data we have just generated, and yes, and we are setting the seeds um, so that our explanations are consistent. Okay. Now here what we're doing is we are trying to draw a line, okay, line through the data after doing the prediction using linear SVR. So here you can see that we have done is we have defined some epsilon, okay, and question is, why was epsilon chosen as 0.5? I'll come back to that. Okay, so let's say we choose epsilon 0.5, okay, and we fit it here, and then it generates the coefficient and intercept. And then, okay, so this is the line that it had generated. Okay. And let's just plot the epsilon also. So what we are doing is we are drawing the parallel lines, which are 1.5 from both the sides. So this distance is epsilon. This distance is epsilon. Okay. All right. So now let me, this is okay. Then we have, okay. So the unit of epsilon is same as the unit of y. Yeah, this is the vertical distance. Okay. So I'll tell you, the epsilon is this. Okay. The epsilon is this. If we draw it with the, okay, let me just show you again. Basically, this is what we have done there. So essentially, this part, this distance is epsilon. This is epsilon. Okay, good. Now moving ahead. Okay, so we basically, I think the purpose of this whole exercise is this. So all we are trying to do is we all using this piece of code, all we've tried to draw is this and this. So for epsilon 1.5, this is how our model looks like. For epsilon 0.5, this is how our model looks like. So as we are decreasing epsilon, the violations are increasing. While when we are increasing epsilon, the violations are decreasing. Okay, so so the basic idea is to have a minimum possible epsilon where the violations are also minimum. Okay, so that's the point we have to optimize upon. All right. So now, yeah. Okay. I think that's the same thing we have done here. All right. So that's right, Kamal. So we basically experiment with various epsilons. Epsilon remains as again another hyperparameter. So the goal is to maximize the number of training sets within the epsilon line. Okay. Now, same thing is in this here, where we basically here is the case where it's nonlinear, and so the same thing, the way we did nonlinear classification with SVM, the same thing is possible. same thing is possible in case of nonlinear regression as well. Okay, nonlinear regression as well. So we use the same technique as we did as we see, just that the objective function, the or you can say cost function changes uh, from the max width to min width. Okay, earlier in case of the SVC, we tried to put the biggest width, and here it's just this is the opposite of it. Okay, and the whole principle remains the same, just that the the cost function changes to the cost function changes in order to minimize the street, minimize the width of the street. So therefore, the same, whatever we talked about nonlinear regression, nonlinear classification with SVM, the same techniques apply in case of regression as well. Okay, so now question is, how do we do the prediction? Let me show that. So here it's the same way. Now question is that all right, now how do we do the prediction in this case? Let's say, okay, let's say we have generated this kind of a data, right? This kind of a model is generated. Now, what we want to do is we want to do a prediction at this point. We want to do the prediction at this point. So what we do is we drew a vertical from here, and whatever is the y value from the decision boundary, from this there is a decision boundary still here, and using the decision boundary we do the prediction. All right. So in the case of SVM regression, we have a decision boundary and we have the support vectors, as in we have the basically the margin. Okay, so we do the prediction based on the decision boundary. Okay. All right. Now let's just okay. Good. So in case of the SVR, which is SVM regression, we use the same kind of mechanism that we used in case of SVC, just that we use the SVR here, and we have one more hyperparameter called epsilon, and yeah, again the C remains as still the regularization parameter, though C signified different thing earlier. Now here C is and basically the regularization parameter. It's not this width of the street. It's not that width of the street. It is basically a regularization parameter, while the epsilon is the one that is dictating the margin. Okay, so all right. So this is the example of how it has fit the quadratic results. So below it, we are generating a quadratic data. So let's say our basic equation was this, and we have generated the data, which looks like what do you say, parabola, and then we basically computed here at this point. At this point, we run the SVR, and then we did the fit. Afterward, we did the predict. Okay, and then we drew these values of y, but we did the prediction of x's, which we have generated as a linear space here from -1 to 1. We have generated x, and then we have done the prediction, and then we have drawn that plot. Okay, that's what we are doing. Again, we are drawing the margin boundaries just to display how it looks. All right. So in summary, wherever we used SVC earlier, in the same way we can use SVR. Okay. Rest of the things remain as such. All right. Now, all right. So here is a comparison. Here is a comparison of um, various parameters, various hyperparameters. So here, let's say the epsilon was 0.1, which means it was thin. There were more violations, while there were more violations, and when epsilon was bigger, the violations were lesser. Okay, and the plot was, this one was less accurate because it is kind of accepting all the dots. Okay, and here again there is second parameter called c, in which when c was really small, right? C was really small, then it basically, for the same epsilon, when c was small, it basically did a lot of more violations and basically did and skipped a lot of random data. So yeah, so this is what we did. Basically the curve was flatter. Okay, so if the epsilon is higher, there will be less number of instances of the street. If there are, c is higher, less number of instances of the street. So okay, so both epsilon and c, if both are higher, then there will be less number of less number of instances of the street that we can see. So if the epsilon is higher, there are less number of violations. There are less number of violations here if the epsilon is higher, and if c is also higher, c is higher, like in this case, there will be less violations, while in this case there are more violations. Okay, that's something which we need. However, if we so higher epsilon and less number of violations does not always imply better model. Okay, so if we increase c, it could lead to the overfitting, right? So here you can see that it is kind of overfitting when the c was higher. It's kind of here, it's kind of skipping a lot of data. So it's kind of overcoming the overfitting. All right. Now, yes. Now, so the linear classification basically, so these are the things that we have learned so far. We discussed about we started with the discussion with bad model versus good model, different lines that we drew in case of classification. Then we talked about feature scaling. Then we talked about the hard margin versus soft margin. Then we learned the nonlinear SVM classification by adding similarity features and polynomial features. And then we did a comparison of complexities of SVC, SVC linear, and SGD classifier. Okay, and in SVM regression, we have just talked about basics of using the linear SVR and controlling the width of margin using epsilon and using kernelized SVM regression model to nonlinear models. So If your data is complex and your linear SVR is not giving good results, then you should generally go with the kernelized one. Uh, and you could also try by adding the polynomial features. Okay, so all right. I'm thinking that though we would like to learn what is kernel and how it actually works, the algorithm that we have been skipping. Okay, so should we learn this, or should we keep a separate class, because this is going to be just too much mathematical? Okay, so the under the hood, actually, that's what we're going to talk about. Or should we move on to our next topic and then discuss it maybe in a separate class? What do you say? Okay, a question from Noor was that which one, in your opinion, was the best graph? Okay, so let me just, okay, let's just go to the, okay. The best graph would be the one which is giving predictions really well on both the data on cross validation. Okay, and okay, so for example, here, this is definitely not good. This is definitely not good because it's kind of making it look linear. It's fitting entire thing when the C is lower and epsilon is lower. While these two look good, these two look good, and this one is the best out of these four, because this one has smallest number of violations, as well as it has a smallest epsilon. Okay, so it has less violations and less epsilon. So this is kind of good. Okay, and yes, let's just, you can actually run it and then compare the results. Okay. Okay. All right. A suggestion from Ross is, okay. All right. So in this, in my opinion, this is the one which is good. All right. A suggestion from Ross is that I would request covering additive regression. Let me make a note of it, and let's just include it maybe in a couple of sessions later. But okay, good, great. Now, yeah. So should we go into the details? I would suggest that we should keep it as a separate session, and because it's going to be a little bit more mathematical, and even if we are not aware about the under the hood thing, we should. Okay, all right. So let's keep it in a separate session. Okay. A question from Noor is that, so in this case, it is overfitting, but giving good results. Yes. All right. So yes, it is kind of overfitting, giving good results. So we can actually compare their predictions. We could compare their coefficients and compare that with our original one. Okay, where is the original one? Yeah, compare these, compare the predicted coefficient with this one, or we can just do the cross validation. That will also be good enough. Okay, great. Now, great, great. So should we start with decision trees? All right. So in this session, we are going to learn about decision trees. Decision trees, okay, before jumping into this, let me just share the slides with you. Okay. Okay, so keep the slides with yourself. Do not share it with in the public, okay, with others. And we do plan to make these slides public maybe at a later point of time. Okay. As in, we are trying to figure out how can we make these slides as open source, and so that people around the world can teach using the same slide and contribute to it. So that's what we're trying to figure out. Okay. Now, so in this session, we are going to talk about decision trees. Basically, they are, oh, it is asking permissions. I think this is the same problem. Okay, can you try now with the and Pavan? Wonderful. So decision tree is a, a very interesting topic. It's a very interesting topic, and because the one that we learned in the first session in the end-to-end project was actually the decision tree. It's very powerful one. The random forest was basically nothing but many decision trees together, or ensembled decision trees. Okay, so decision trees are really versatile, and they can perform classification, regression, and even multi-output tasks. Okay, so they're capable of fitting complex data sets. Okay, now let's just, okay, yeah. So let's take a look at the decision tree example. So here is a very simple decision tree that goes in our mind. Okay, should I accept a new job offer? Should I accept a new job offer? And here, if you see that this is basically a inverted tree, like most of the trees in the data structures or algorithms, it is like that. It's an inverted tree. So here is a model. This is basically a model which we have in mind, and against that model, we we basically we basically do the prediction. We do the prediction based on this model. So in our mind, we have, let's say, this model, and let's say there is job offer. So we will first check whether is the salary at least 50,000. Yes, then we go here. No, we decline the offer. Okay. So is commute more than an hour? If yes, decline the offer. No. Does it offer free coffee? Yes or no? So this is one example of the model. Okay. So question is, the thing that we're going to learn in this session is how to create such a model given the past experience, right? We have created this mental model based on our past experience or past learning. In the same way, how to create this kind of a model, right? Because if let's say we got a salary of say there is a job which is having a commute of half an hour and offering $60,000. So how would it happen? We'll first check whether salary is this much. Yes, then we'll go here. The commute is half an hour. That means no. And then the last make or break will be the coffee. Okay. So basically this is the decision tree, which there could be, so how many features are there? Salary, right? Salary is one feature, commute is another, and coffee is another. So there are essentially three features on which we have built this. All right, now we are going to learn all of these parts. We will train, visualize, and make predictions with decision trees. We will learn the algorithm underlying called CART, and then we will learn how to regularize trees and use them for regression tasks, and then learn how to do the regression with the decision trees. Okay, and okay, then we learn the limitations of decision trees. Okay, a question from Bintao is: are there only two decisions? There may be three. Come out. Yeah, there may be three outcomes. Yes, yes, no, maybe. And as a matter of truth, basically we put a probability here. We put a probability here, and therefore, and that's how we convert. That's how we convert decision tree from classification to regression. Okay. 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 So Ross used to do manual decision trees for support personal products. Wonderful. Wonderful to know that. All right. Now, let's move on. This is a very interesting topic. So, because there's something that goes on in our mind, it's like very much like the way we take decisions. Okay, so let's just build a decision tree and take a look at how it makes predictions. We will train decision tree classifier using scikit-learn on the famous iris dataset, and then we'll see how it works. Okay, so iris dataset had four features, remember? The petal length, width, sepal length, and width. And there are three classes, namely Setosa, Versicolor, and Virginica. Okay, this was the dataset, right? And okay, so it basically had four features, and here we are going to only use petal length and petal width. Okay, we're going to use only petal length and petal width. So we'll follow the following steps to train and visualize our decision tree. So we'll load the iris dataset. Okay, so we'll load the iris dataset. Okay, okay, it's not there, so I'll have to go to my console and pull the fresh one. So cd ml cd machine learning and say git pull. Okay, it says that we need to do git checkout. I'm overriding my changes. Okay, git checkout. Now I can do git pull. Good, now it worked. Okay, so we have decision trees. Okay, so this is what we're doing here. We basically, first of all, okay, so we are using the load iris method available in the data set, and iris is our data set here. So let's just take a look at iris. Okay, and here is the description, and iris dot keys is this. Okay, so it has these many keys because iris is a dictionary of dictionary of key value pairs. So we would be interested in knowing data and target. Okay, so and if you want to know the names, we'll just use the target names. So here we are saying that consider only the petal length and petal width. Okay, so X is our those two features. So let's just take a look at iris data first. Okay, so iris data is this. So we are saying give me okay, let me just take a look. All right, give me all the rows and only two columns after. Okay, so that was feature names. If you want to know what are the feature names, so we can use the feature names. Not like this, we have to say iris. Okay, so we're going to ignore the sepal width and length for now. We'll just take care, use petal length and petal width. That's why we are saying give me 2 onwards. This is 0, 1, 2, and 3. So here X will contain the last 2 columns and Y will contain the target values. Now, here we have here we are using this reasonably classifier. Okay, and this is the hyperparameter that we're passing. We'll talk about these things, this particular parameter later, and then we will fit. Okay, once we have generated our model here, then we can use it to, you can use it to present. Okay, so what we can do is we can export the results of tree CLF, okay, to iris tree dot dot. The dot is a general format, and GraphViz is again a very good tool to visualize the graphs. Okay, it's an open source tool to visualize graphs. So we are using export to GraphViz that will present. So here basically this file contains our image. Now using here, why we are doing this, because there is the matplot doesn't have a quick way to present this kind of a tree. Okay, now we're going to use this command to generate convert dot format to PNG format. Okay, so all right, so I think it has, yeah, this is that image. Okay, so iris tree is the image. Let's take a look at it. This is the image. Yeah. Okay, so this is what we have done. So we used, we in the terminal, we converted dot format to the PNG, and then we went to the browser and clicked on it, and then it shows us this diagram. All right. Although it's not really needed. Okay. A question from Binta is how to run the code to obtain your new script in Jupyter Notebook. So all you have to do is you just go into the terminal, okay, here. All right. So in your home folder, wherever you had checked out, go to that place. In my case, when I did clone, it created ML folder, went to that ML folder, and then went to the machine learning. Okay, and then did git pull. It threw an error showing me that you need to check out the particular one, whichever. So your changes, either you could copy them somewhere, or or you could, mm, you know, just overwrite it using git checkout. Git checkout basically overwrites your local changes. All right. Gigi and Bintao, are you able to do it? Okay. Yep. So question is, can I just run this? Let me just try. Yeah, you can put an exclamation and run it. Okay. Let's say, let me just delete this file. Okay. You can put an exclamation and then run it. Yeah. Okay. So in your case, there is these all files you have changed. So what I'll suggest is make a copy of say machine learning folder. Okay. So make a copy of these files and then do a git checkout on these files. Okay. So all right. If you want, I can take a look at your screen so that others can also. Yeah. Okay. If you're okay with overwriting, you can just say git checkout and then do star, and then it will check out everything. Yeah, that's also good. What is Ross suggesting? Yeah, yeah.
Grim?
Yeah.
Hello?
Yes, I can see.
But you see, I tried, you see, I try it.
Mm-hmm.
Cool.
Mm-hmm. Good, good.
Let me check
It
this.
worked. It worked. So when you did git checkout, it basically overwrote your changes and it worked.
I don't finish yet.
I think it finished. Scroll down. Yeah,
Okay.
it's finished.
Let me check here. Where is decision tree? I don't see decision. Oh, it's here. Thank you.
Okay. But I can't see. Oh yeah, this entry is there. A question from Noor is it possible to have our local repo sync with two remotes? Yeah, you can do that. You can basically add different origins, add an origin. Okay. You can Actually, yeah, you can change the origin and do that. A question is there a way to do that? Okay, yeah, that's just one thing I was thinking about. Is it possible to display this image right from here? If I use cat, will it work? Or it did not work? Wow, it kind of froze. Oh, it froze. All right. Gigi, are you able to do that? Should I? So, do you want to show the screen? Okay, please go ahead. Okay, it is saying that, so do you want to keep the changes because you have, you must have when you run the notebook, every time we run, you make generally changes to that. So do you want to keep it or do you want to delete it? Do you want to keep or do you want to delete, Gigi?
Hello.
Yeah.
Yeah. I don't want to keep it.
Okay. Okay. You can say git space checkout. You can say git space checkout.
Okay.
Space dot. Now say git pull. All right. So it has done that.
All right. Thank you.
Great. Great. So now I can show my screen. So here we are. So yes. So now we have done everything inside the notebook itself. Okay. Instead of running in the terminal. So you can actually do exclamation and okay. It's not, yeah, you can do exclamation and then followed by any command and you can get the results. Okay. And also, yes, the one suggestion from Noor was to use this. It actually worked well. So we used Python display and we displayed the image. Okay, great, great. So you can see that here. Let me start from the beginning because I restarted my kernel. Okay, after I tried to do cat, it actually froze. Okay, this is ls and then dot and then okay, great. Now, all right. So when we do not give this, we're going to create the image in the same folder, as in this one is going to create the image in the same folder, as the notebook, and so on. Right now, good. Okay, we can remove this. We can remove this. All right, I like to push this change. Should I push this change so that git diff? Okay, so it shows git commit -m. We say okay. If we are saying what did we do? We basically made made image creation from git push. Oh, it's not. I'll have to add the origin and all. Okay, never mind. Good. So now let's move on. Now this is what we did. Good. Now let's learn to do the. Yes, go ahead, Noor. That's correct, Noor. When you commit, it commits to your local repository, not to the GitHub. That's right. So I think I got your question, the question that you were asking earlier about how can I do both, right? Retain my changes as well as those things, right? So there was a question, right? Let me just, I think this could be one of the approaches which we could follow. Then let's say there is CloudX Labs ML repository. You could basically fork it and have, say, Noor/ML. Okay, so you could fork it here. Okay, there is a feature called fork, and then you could check out from here. Or you can clone from here. And so when you clone, right, in the local system, you have two places, right? One place is local repo. This is everywhere there is a local repo. Okay. And here, this is your working environment, right? This is basically a working environment. So, and when we, right, when we are, say, doing checkout, this is what is happening. Okay, so checkout is this, and okay, so git clone or pull is bringing from the remote. Right now we are doing it, we all are doing directly from here, but you could try this also, okay, by forking. So, and from here to here, it's basically push, right? Push. And here, this is when we do commit, it's actually local. Okay, I think this gives you a clear picture, right? Okay, so yeah, our question is when we want, how do we update our remote? So basically here, the only challenge which I foresee is in this phase. You could always do the merge. Okay, you could always do the merge. There is, how did I do the merge earlier? It's actually pretty simple process. You can actually merge here. So when you're merging, it'll show the conflict, and when you and then you'll have to resolve those conflict. Okay. Okay, let me just read your question again. But since you are not replicating to GitHub, then how will I get changes to my local environment? Okay, my question from Noor is, so if I want to replicate these changes to my local environment in the machine, not the, okay, good, good. So what you can do is actually install GitHub on your local machine, okay, local machine, and then, a Git desktop is there. There are any Git tool that you can do. Let's say my Mac right here, this is my local Mac. So I can actually do git clone and clone the repository from here. Okay, I can do that. Is that your question? So you can actually do the git clone from here, and if you're on Windows or even on a Mac, I kind of find Git desktop to be really useful, or GitHub desktop. Okay, yeah, this is the one that you could use for the desktop. A question from Nuri, but that requires you to replicate your changes to GitHub. Not really, not really. You could just keep on git pull. Okay. All right. So I think this would be helpful to you. So generally, this is what people do with the repositories, that they generally fork and keep on merging. The only challenge which I see in case of our kind of model is that merging two Jupyter notebooks is little difficult, because the output also is a part of the Jupyter notebook. Whatever code we type, the output of that code is also part of the Jupyter notebook. Therefore, merging is a little harder. Yeah. Okay. So yeah, maybe somebody could just share a cheat sheet of Git. That'll be useful. Okay. All right. So should we start? So this is the visualization that we generated. Okay. So this is the decision tree automatically generated by the algorithm, and this is what we are going to use in order to classify. Okay. So here what we see is the node's value attribute tells how many training instances of each class this node applies to. For example, the bottom right one applies to 0, which is the bottom right, yeah, here 0 as in Iris setosa, 1 versicolor, and 45 is virginica. All right, so what are we trying to do? We are trying to do classification. We're trying to do classification of the Iris data set, correct? So we trained our algorithm, and what it has done is, here it has said value. There is a value attribute, and the value attribute is at the top level. It says before applying this logic, it could be that there are 50 instances of each. Okay, while on this rightmost one, it says that there is, if somebody comes till here, the chance of it being it is most likely that it's going to be the virginica, right? For 45 out of all, right? So Gini value is indicator. We'll talk about Gini soon enough. Okay, Gini is kind of a confidence label. So the node's Gini attribute measures its impurity. A node is pure if Gini is 0, if all training instances it applies to belong to the same class. For example, at depth 1, okay, so you can see here the places where it's very clear, right? It's very clear. Then the Gini is really low. When it's 50%, 50 of, here it's very clear that there are 45 instances of Virginica. So every node in the decision tree is is basically uh, deciding whether to go this way or that way. Okay, let me just explain this and come back again. Okay, so here the Gini score is going to be 0. Why? Because it's totally confident that 50, there are 0 instances of Setosa, 0 instances of, sorry, 0 instances of any other thing. All of these are 50. Okay, so if the petal length is lesser than 2.5, okay, if the petal length is lesser than 2.5, then this, otherwise this. We further say that if petal width is lesser than or equal to this, then go this way, otherwise go this way. So this side, when petal length is 2.45, the node is clearly having only Setosa as the Setosa in the training set. Okay, so to make a prediction, a decision tree classifier follows these steps. Start at the root level. Okay, start at the root level. The node asks a question whether a flower's petal length is smaller than or equal to this, and then move. Okay, and then it moves down. Okay, and if not, then you move to the right. Since it is a leaf node, it is not a leaf node. It asks further questions, as in the what is the petal width? If it is less than 1.75, go this way or go this way. Okay, so this number of instances actually kind of measures the probability of something. Okay, while the tree was created, this is how the division was done. Okay, and here it says that the when you come to this side, there is a probability of various things. Okay, all right, so this is basically an example of decision tree. All right, should we take a break and then come back to the question? Before that, there's a question from Binta. Where does it come from? Dot. Okay, so dot is a program. It's a general program. It's a pretty useful program. Okay, to convert to deal with dot files. Okay, so dot is a raw format, not like PNG or JPG. Dot is a raw format for graph representation. To convert a dot format, we are using a command called dot. Okay. So yes, so let's take a break for 10 minutes and be back by break for 10 minutes. I'm back. Should we start now? Hi, everyone. Should we start now? All right. So, so, right. So what we did was, as part of this, what all we did was we basically created a decision tree classifier using our iris dataset based on the two features. the petal's length and the width. And then once we trained it using fit, then we presented the model. We presented the model and okay, why max depth 2? Because we wanted only the tree till the 2 depth. Okay, difficult to present it in more details. Okay, so what it figured out that if the petal length is less than 2.5, then it's definitely setosa. Otherwise, it could be the versicolor or it could be virginica, right? So that's what it figured out. And then further, it figured out that if petal length is less than 1.75, the chance of it being the being the versicolor is high, while if the petal width is greater than 1.75, then the chance of it being virginica is really high. Okay, so it generated this model based on our data. Okay, now with this we could do predictions. We could do predictions. All right, the Gini score is how pure are the prediction. How clear are the prediction? You can see that this one is 100% pure, as in it is, the value says that here on this side, 50 are setosa, 0 are the versicolor, and the 0 are virginica. While at this point, it shows that 0 are the 0, the on this side of the decision, or this side of the this side of the tree, on this branch, 0 are the setosa, while versicolor are 49, while 5 is virginica, right? So, and of course, that is making it impure. So it is, therefore, the Gini value is higher in this case. Okay, here the further the impurity is less. There is only one instance of versicolor on this side, therefore the Gini value is small. Okay, now let's go ahead and okay, right? Now decision trees basically has something called boundaries, right? Lesser than this, then greater than this, right? So here the petal length is one feature, petal width is another. So it has drawn the boundary like this. The first one, it says petal length. This is first boundary. Okay. On the left hand side of the boundary is setosa, right? On the right hand side, it could be other things. Then it further draws another boundary, this time based on the petal width, this time based on the petal width, right? And then lesser than this value is here and greater than this. And further, if we had more depth, it could keep on dividing these into further boundaries. Okay, so basically all it does is it kind of does the internal classification. Basically, it keeps on dividing the data based on certain parameters. Okay, so that we can easily use it for either classification or regression. All right. Now, node's Gini impurity is the measure of its impurity. A node is pure if all training instances it applies to belong to the same class. The Gini coefficient of 1 expresses maximal inequalities among the training sample, right? So if Gini coefficient is 1, like there is no 1 here, okay? So the the Gini coefficient would go max up to 1. It can't go up to, it can't go beyond. Okay, now this is a clear formula how to compute it, and the formula is basically 1 minus the ratio of each, 1 minus the sum of ratios of each. Okay, so like in this case, it's, what is the ratio of this? 50 by 150. 50 by 150, 50 by 150, that is 1/3, 1/3, 1/3, right? And no, actually it is the, okay, I think, yeah. So pi is the two, okay, it's a square of it. That's one important part. It's a square of it. Okay, it's a square of it. So 1/3 square plus 1/3 square plus 1/3 square. That's what it is. So here it's, all right. So that's how it is. So here it's 50 by, did we do the calculation? Yeah, here. So is this formula clear to everyone? 1 minus from I equals 1 to C as in all possible classes, and then pi square. Okay, what is pi? Pi is the ratio of class I in the node whose Gini index is being calculated, divided by total instances. Okay, say for example here it's basically 0. So, and let's try to compute for depth 2, the left node, this one. It is 1 minus, right? 0, how many total instances? 5 plus 49 plus 0, which is 54. So 0 by 54, the whole square, minus 49 by 54 square, and 5 by, you can see that. So 0 by 54, 49 by 54, and 5 by 54. Each one of them is squared, and that's why it has calculated 0.16. Is the Gini score clear? So Gini score signifies how confident or how clear is the classification. The smaller the Gini score, the better it is. Yes? Yes. Gini score is for the verdict. So Gini score is what the prediction is all about. Like in case of here, you see that? In this case, it's a draw, right? Here at this point. So it's 50, 50, 50. So Gini impurity is really high in that case. So 50 by 150, square of that, then 50 by 150, square of that, and so on. Okay. Okay. So the more clear is the indicator, more clear is the model, the better would be the Gini score. Okay. More the clearer are the predictions, the better would or you can say the better is the smaller is the Gini score, the clear is the predictions. Correct. So higher value means it needs more features to draw, or more data, more features or more data to get a good conclusion. Okay. All right. Yes. So it basically needs that there would be more leaf nodes below a particular node if the Gini score is really high. All right. Very good point, Noor. Okay. Kamal, all okay. So it states the verdict of as any of the, yeah, correct. Moving ahead. So this is how we calculate the Gini impurity, right? So remember that it's a square. So square of the fractions. Square sum of the squares of fractions. Okay. Now we'll earlier as we go ahead, we will also talk about something called what is white box, black box. So white box model is generally fairly intuitive. The decisions are easy to interpret. And an example are descent trees. Descent trees are very good, very easy to interpret in the production. A question that people ask me generally when in machine learning sessions is that when we do something using machine learning, okay, how will we debug? A general question is that in case of production environment, when something is going completely haywire, and how will we debug? And that's a big fear which we all have, that that in case in production, if my machine learning algorithm starts misbehaving or it starts misbehaving, we should be able to figure out why it is so, right? And that's one of the very important criteria of using certain algorithm versus another. Because if the engineers are not confident about a particular model or particular algorithm, they would not take it to the production. Okay, so that's why the white box, as in the algorithms which are transparent, which are easy to interpret, they are preferred over the ones which are black box. Okay, and the only thing is that sometimes we might, because of the fear of the unknown, because of the fear of unpredictability, the we kind of let go of accuracy. Okay, we kind of let go of accuracy, and that's why white white box models are generally preferred by many people. Okay, so that's another criteria other than accuracy, but how transparent or how easy are the results, how easy to interpret are the results. Okay, so while the black box model is, they make the we have many black box models, so they make great predictions, and they're easy to check the calculation that were performed to make these predictions. Okay, so even though black box models give great predictions, and but 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 the model that it generates is hard to interpret. That's why it is called the black box. Okay, it's usually hard to explain in terms of why predictions were made. The examples of black box model is neural network, and even when we ensemble a lot of decision trees together on random samples, that becomes random forest, and that also becomes hard to explain. So as we try to increase the accuracy, we would be in a situation where the results are harder to explain. Okay, so eventually we kind of have to make peace with, I mean, we have to have a trade-off between the white box versus black box. Okay. All right. So this is the diagram that correctly puts it. Okay. So the white box approach versus accuracy. So on one side you have as the interpretability increases, it's more of white box. If the interpretability is low, it's called black box. Okay. Now the decision tree is a white box model because it shows that, but when you ensemble decision tree and have many parameters, then after a point of time, it kind of becomes black box. A question from Kamal: all that we have learned till now, SGD, SVM, are white box. Yes, more or less they are white box. But SVM, after a point of time, when you put more parameters, it also kind of becomes black box. Okay. As we will learn that, as we try to improve accuracy, okay, and the objective of these sessions that we are running is that we become comfortable with most of these algorithms so that they don't look black box to us. Okay, they don't look black box to us. And basically that's one of the reasons, although, right? So even though e- even though you can get, you can actually start using all kinds of algorithm right away, but to make yourself really comfortable, it's important to understand what goes below the under the hood. Okay, so yes, so white box versus black box is kind of debatable and is subjective term, right? It is also from person to person based on their understanding. It is also based on how much fine tuning we have done of the same algorithm. So it's a little more subjective term. Okay, so the criteria, the reason of these sessions is to make things look more white box than the black box. Okay, now moving ahead. So a decision tree can also estimate the probability that an instance belongs to a particular class. So not only for classification, the decision trees could be used for regression. Okay, and that's where we use the probability. So a decision tree can estimate the probability that an instance belongs to a particular class. To do this, it follows the following steps. First, it traverses the tree to find the leaf node for that instance. Okay, then it returns the ratio of training instances of class K in this node. Okay, say suppose you have a flower whose petals are 5 centimeter long and 1.5 centimeter wide. Now, what is the probability of each of the classes? Okay, so you say 5 centimeter length, so it says, okay, go to the right, 1.5 centimeter wide, so go to the left. Correct? That means that it could be versicolor or it could be Virginica, but being Virginica, it is going to have a very low probability, right? So the probability of the versicolor is 90.7, which is 49 by 54, correct? And the probability for Virginica is 5 by 54, that is 9.3%. So you can see that it basically is giving us the probability of probability distribution amongst the various classes. So this one has the lowest probability. This one has the lowest probability, which is 0. This one has second highest, and this is the highest probability. Therefore, it is versicolor. Now, so we can ask, if we ask to ask it to predict the class, it would output the versicolor because it has the highest probability. We can also ask it for predict prob A. Predict prob A. Okay. All right. Let me just run it. Okay. Question from Midda is, how can I check what does AARY1 stand for? This one, the result of this one. Okay. So what we do in this case is, I'll just do that. So I'll say probability equals this. All right. This is the array. Okay. And probability, you can see now I can do 0 or 1. Okay, it says the array is out of bound. Ah, it is actually an array of arrays. Okay. Okay, because it's expecting that you might have asked for multiple inputs. Okay, therefore it has given us array of arrays. Okay, did it make sense to you? So the array 1 means the prediction is that it is only, I'll tell you. So what does it mean? It's predicting that which class is it? Which class is it? Right? That's what it is predicting. So array of 1, because you could have asked for multiple flowers, right? You could have asked, say, things like this. Therefore, okay. So it is 1. 1 means it is 1. That means let's go up. Okay. So this is the target that we had chosen, right? And target names is the names that it will give you. Okay. So what is the name of data? It is iris and target name. Okay. So 0 and 1. So it is versicolor. Good. Wonderful. Great. Great. All right. So the under the hood, scikit-learn uses an algorithm to generate this model. This tree is basically a model because it's able to classify an input and classify correctly. Okay, so scikit-learn uses the CART algorithm to train decision trees. CART means classification and regression trees. The idea is quite simple. The algorithm first, so algorithm needs to split, right? So what it does is it would split the training set into two subsets using a single feature k and a threshold dk. Okay, such that it produces the purest subsets. Okay, now so it has to pick the threshold, okay, and a feature. On the basis of that feature, on what point should it break? This number that it has done earlier, this point that it has broken, this is that feature's particular value. Okay, so at what point should it need to break using a single feature? At which point should it break such that it produces the purest possible subsets? Okay. Okay, so the cost function that the algorithm tries to minimize is given by this equation. Okay, it's given by this equation. Here, what he's saying is m of left divided by total m, which is number of instance on the left hand side divided by total instances, multiplied by G. G is the measure of impurity on the left. And so it's basically the weighted average of the impurity. Okay, so the total number of instances on the left multiplied by its impurity, and then total instances on the right multiplied by the impurity on the right, both divided by total instances. So it's essentially kind of weighted average of the impurity. Okay, so this is what it tries to minimize, as in the less the impurity, the better it would be. Okay, so once it has successfully split the training set into two, it further splits the subsets using the same logic. Okay. So it stops the recursion once it reaches the maximum depth defined by max depth parameter, or if it cannot find a split, that will reduce the impurity. Okay, at that point of time, it will stop going down. So first it will kind of guess this value by trying to change this value from 0 to some value. And once it has done that, once basically it has split it, then it will compare the overall Gini impurity on the left, overall Gini impurity on the right, and then compute the summation, multiply this by instances, multiply the instance of the right, and so on. So this is what goes on. This is what goes on in generating the descent trees. Okay. All right. And it keeps on doing it until it reaches the end. Question from Kamal. When there are multiple features, how does it decide which features and boundary to choose? Very good question. So it would try both the things. It'll pick up a feature. It'll pick up a feature, try to find a boundary, then it will pick up the second feature, try to find the boundary, and compute the minimum overall impurity. Okay, so whichever feature is giving a lesser impurity, it chooses that feature and that feature's value. Yes. So yes, it will try a lot of combinations. Yes, so it'll have more, it'll have a huge complexity, but the same is true with almost every algorithm. Okay, while prediction is really fast because it has to just keep on going down the tree, and it's really fast, but training might take some time. Okay, so a greedy algorithm, so basically it does not check whether or not to split will lead the, okay. All right, let me go ahead. So it is a greedy algorithm as it greedily searches for an optimum split at the top level, then it repeats the process at each level. It does not check whether or not the split will lead to the lowest possible impurity several levels down. Okay. A greedy algorithm, so it does not do all possible combination, that it'll also split it and then see if the previous split was better or not. So it doesn't do the backtracking. Okay. So a greedy algorithm often produces a reasonably good solution, but it is not guaranteed to be optimal. Okay. So is anybody else having the audio issues? Is the voice clear to everyone? Okay, we'll come to entropy just in a minute. Okay, good point, Pawan. Now, so the complexity of prediction is something that let's discuss. Making predictions requires traversing the tree from the root node to the leaf. Okay, these trees are generally balanced, as in the tree is having equal kind of node on the left and right side. So traversing a decision tree requires going through kind of log m nodes, okay, where m is number of training instances. Why? Because it's more like a binary search. What is a binary search? That you search for a value in the, you compare the value with the middle of assorted numbers, middle of the list of sorted numbers. If the value is lesser, you go to the left, otherwise you go to the right. So there also, you keep on dividing the data set into approximately 2 equal parts. Here also, we will keep on going down the tree as we perform the comparisons, and therefore the overall performance of decision, the the speed of prediction is really high, as in it's able to do the prediction really quickly. And the reason is the total number of comparisons are total number of what do you say, time complexity is going to be the log m. Okay, where m is the total number of training instances. All right. Instance is like the data points. Okay. Okay, let me go back. Yes, number of data, input records. Okay, so in our case, there are 150 input data records in this case, input data. So this is, where is, yeah, here, let me just show you that. So what was the iris and data, right? So you can see 150. All right. Okay, so Kamal is saying that splitting on the basis of feature k and threshold value of tk, right? So what it does is it picks up a feature, finds its threshold value such that both you get the purest subsets. Okay, that's what is the purpose. Okay, a question from Minta is, log m is a large number? No, log m is a really small number. Okay, it's proportional to log m. Okay, so yes, m is equal to the total number of instances. And how do we compute? I think, right? So I can just show you here. So if let's say you have even these many instances, the result is 11. Okay, the result is 11. All right. So to very huge numbers, the log is generally really small. Okay. Right. So Binta's question is that if log 2 of 32 is 5, yes, so 5 new nodes or roots. In the worst case scenario, in the worst case scenario, there will be 5 total nodes. Okay, 5 total comparisons. Okay, all right. Yeah, threshold is basically for the boundary. A question from Noor, is there a way to exclude certain features to be included in an algorithm in order to make it fast, or do we have to remove those features from the dataset? Okay, the reason for excluding these features would be from past experience that these are irrelevant and won't add any value. Okay, so yes, so it's generally better to just remove it from the input data because most of the algorithms do not give you this functionality of excluding the features, right? That's one of the reasons why we use the NumPy in many cases, because slicing the features is, or slicing the array is extremely fast. It's a very good point. Yeah, it's a very good point. So, okay, a question from Kamal. Um, At each node, the splitting is always based on one feature. Yes, as per this particular algorithm, the splitting is based on one feature. All right. In the decision trees, the splitting is generally based on one feature. Right. Because the other one, let's say the other second feature we have, if there is a second feature, then that second feature will come into play as we go down the particular node. Okay, so far I have generally seen the in the case of a decision tree, the single feature based division is something that we have seen. We'll see it even later if there are any, but I've not seen more than a single feature based decisions. All right, very good questions. Okay, now a greedy algorithm often produces a reasonable good result, but it is not guaranteed to be optimal. Okay, so it does the splitting based on the current scenario. It doesn't do the backtracking in the sense that it'll further divide and then go back and try to optimize again. Okay, it doesn't do that. It basically do not worry about what will happen after several levels down. Okay, so making predictions requires traversing the decision tree from the root to leaf, and therefore decision trees are approximately balanced. Therefore it is generally faster. So had it been unbalanced, then it could have been really slow. Okay, imagine a tree like this. Okay, unbalanced could actually cause a lot of slowness in it. Okay, so if let's say, okay, I'm just trying to draw um uh you know this kind of a tree. Okay, so see that? So basically, if you see, it'll come here, then here, then here, then here, and then here. So if the tree is unbalanced, like completely towards the right, what will happen is it'll end up doing a lot of work. It'll become kind of O(n), okay, instead of O log n. So therefore, the trees need to be balanced in order to search. It's similar to like binary search tree in that sense. And so region tree requires going through roughly O log m nodes, where m is total number of instances. Okay. And since each node requires checking the value of one feature, the overall prediction complexity is just O log m. Okay. So here we checked one feature, then another feature, and so on, right? So complexity of prediction is generally independent of the features. So predictions are very fast even when dealing with humongous training data sets. Okay, the training algorithm compares all features on all samples at each node. Okay, so what it does is it basically compares all features on all sample nodes at every node. If there are n features, it is going to take this much overall complexity, right? So if this is the label, so m into log m into n, right? That's what it is going to take, where n is the number of features, and we have to compare all n features at each of the m nodes. So for small training sets, less than 1,000, scikit-learn can speed up training by pre-sorting the data. If we order our data based on the features, then the overall it will basically improve a lot. Okay, but it will slow down training considerably for large training set. So since we will explicitly train upfront, it might take some time to train. Sorry, since we upfront will sort the data before training, therefore the sorting itself might take a lot of time. Okay. So by default, the Gini impurity measure is used, but we can also select entropy measure instead of Gini. Okay, we can just pass this hyperparameter called entropy. Okay, entropy means degree of randomness. Okay, so it's basically a slight different objective criteria. Okay, so here is the formula for measuring the entropy. The entropy measure is pik into log of pik. Okay, so let's take a look what it means. Okay, let's take a look. Let's take a look of here this node particularly, right? So pik, which is 49 by 54, log of the same thing, and then the second one is 5 by 54 and log of the same thing, right? So this is the entropy at level 2. Okay, so what we do have is basically we instead of normally summing up the fractions, we're basically multiplying each fraction with log of the fraction. So okay, so in practicality, it is not much of a difference between the two, between the impurity and entropy. Okay, they basically lead to similar trees. While during the training, if we use entropy or Gini, either of them as our cost function, then it'll lead to the almost similar tree. Gini impurity is faster because there is no logarithm to compute. It's only the square we need to compute. So it's a good default. However, Gini impurity tends to isolate the most frequent class in its own branch of the tree. Okay, so Gini impurity tends to isolate the most frequent class in its own branch of the tree. Okay, so if there is a particular class, because it squares the value, so it kind of emphasizes the pi a little more than what entropy does, and therefore it tends to isolate the most frequent class in its own branch as an observation. The entropy tends to produce slightly more balanced trees. Okay, so that's the advantage of using entropy, that it gives us better, slightly more balanced trees, while it has been observed that Gini impurity tends to isolate the most frequent class in its own branch of tree. All right. So, if we do leave the decision tree unconstrained, as in if we do not impose things like max depth is 2, if we put it like max depth as something high, then most likely the decision trees end up overfitting it. A question from Noor is, can you please give an example of situation where entropy would be a better choice over Gini? All right, that'll be a little harder right now. So let me think. Okay. So if your training instances are really high and you want to make it a little better, faster, then you should choose Gini. Okay. Okay. If your training instances are really high, so you should choose Gini over the entropy. That would be one example. And yeah, I think. And in case your preference is to improve the prediction speed. If you want to still, even though the prediction speeds are going to be higher, if you want to further speed up the prediction speed, you should generally use the entropy, because the entropy as a measure would produce a little more balanced trees, and therefore predictions would be faster. All right. So that could be the case, the two cases. Okay. And now you remember the random forest when we did earlier? It actually overfit. It actually gave us 0 error, and that's when we did the cross validation, right? So basically the decision trees end up overfitting the training data if we do not restrict the decision tree's freedom during training. Okay, so putting restriction on the freedom of the model during training is called regularization. The regularization hyperparameters depend on the algorithms used. Okay, but generally you can at least restrict the maximum depth of the decision tree. Okay, so the models like decision tree models are often called non-parametric model because the number of parameters is not determined prior to the training. So the model structure is free to stick closely to the data. Okay, so since we do not decide upon the parameters upfront, therefore such models are called non-parametric. Okay, because see, maximum depth equals to true is something that we cannot predict upfront. Okay, as opposed to the parametric model, such as linear model has predefined number of parameters such as degree of freedom is. So the degree of freedom in case of linear model is limited. Okay, so all right. All right, so the maximum depth, restrict the maximum depth of the decision tree. Okay, maximum sample split is the minimum number of samples a node must have before it can be split. Okay, so yeah, at which basically while splitting, we can further control the decision tree by specifying these parameters, such as maximum depth. Second is minimum sample split, meaning while splitting, we must make sure that on the left or the right, there should be minimum and n number of minimum samples. Okay, minimum samples leaf, the minimum samples of the leaf a node must have. Okay, so in case we do not tune these, we might end up with a huge depth of the tree. Okay, so and it might kind of do regularization. Uh, it might kind of do overfitting as in memorizing. Therefore, we ensure that it, while splitting the data, it should kind of split it into two parts instead of just start splitting it into one record per node. Okay, that's why we enforce that we must have these many minimum samples on the left and on the right? So yeah, there was one question related to entropy. Let me take a look at that question. Question from Pawan was, does it also calculate entropy on each split? I think that question is answered, Pawan. Okay, I think Pawan is not there. All right, good. Now there are furthermore parameters that you can fine tune. One is minimum weight fraction leaf, same as minimum sample leaf, but expressed as fraction of total number of weighted instances. So 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 basically, instead of telling explicitly the number, we could just specify the fraction. And okay, so here also there is another parameter called maximum number of leaf node. Okay, this is again another one. Now, then there is something called max features. So maximum number of features that are evaluated for splitting at each node. Okay, so these are the various parameters that we can control. So the idea is that we try to increase the parameters whose name starts with min. Okay, so okay, we will try increasing the parameters whose name start with min and reducing the parameters whose name start with max. Okay, in order to regularize the models. Okay, in order to regularize the models. Okay, a question from Bintao, what is the difference between node and the leaf node? Okay, so this is node and this is the leaf node. Okay, leaf node is the last one, while the while everything is a node. Okay, all right. So if we do not leave the restrictions, what will happen is it'll kind of keep on dividing. You can see that here it has even divided the boundary with only few instances. Okay, it's kind of taking care of each and every instance and not letting go of even a single instance, right? This is basically unregularized. There is no restriction. Okay, and therefore it is overfitting the data. Okay, therefore it is overfitting the data. Now the moment in this case when we were training, so what it has done is it has first broken the data set based on x2, and then based on x1. Sorry, first it broke based on the x2 and then again based on the x2. Okay, and here it has no. I think first it has done based on the x2, then x1, then again x2, and then x1. So that way you can see that it is basically here, even though there were one or two instances of blue, it still created the boundary, right? So it's kind of trying to overfit the data. The moment we said keep the minimum samples per leaf as 4, then it ignored this one. Okay, it ignored these points. So basically, this kind of a model, which is more regularized one, it will generalize better. It will generalize better. Okay. Now, decision trees that we have studied so far. Let's just take a look at our. All right. So let's just take a look at this. Okay. Okay. There's nothing to do on the notebook side. Any questions at this point? Balaji, Bintao, Gigi, Kamal, Noor, Pratik, Ras, and Shahrukh? Okay. So basically, this is a good example. So we talked about how does decision tree works, how is the prediction and training happen. Then we're talking about the regularization. If we do not regularize, it will kind of memorize everything. It'll basically keep on creating nodes and further and so on, right? Therefore, it makes sense to kind of constrain it. Okay, so for example here it is not letting go of even single instance, right? Therefore it is memorizing each and everything, and that's what is the overfitting about. Now the moment we kind of constrain the freedom by saying there should be minimum sample leaf this much, then it suddenly makes it more generalizable graph. Okay, so for example, it has ignored this part, it has ignored this, it has, and so on. What does a depth means here? Depth means, okay, so depth of a tree means till what depth should we go? This is 1, this is 2. So overall depth of this tree is 2. Okay, question is that in this particular cases that we are talking about now, what does the depth in this diagram means? How many times further it needs to be divided? So first was this, second was this, third was this. So there is huge depth. So maybe depth would be depth here in this case, depth would be 10 or so. Okay, 10 or so. No, that's not the depth. Depth is the overall depth. Okay, so from here 1, 2. 2 is depth. Had there been more leaves here, like 2 more leaves here, that means the depth could be 2. Okay. Yeah, total from here till the last leaf, till the max, that's a max depth. Okay. This is not, say one is, the depth of this one is 1 from top. Okay. Now, what is the depth in this case? What is the depth? 1, 2, 3, 4, 5. Right? 1, 2, 3, 4, 5. Correct? All right. A question from Noor is, we have many algorithms with many parameters, and again, which one to choose is only dependent on cross-validation. Yes, on intuition experience. Okay, so intuition and experience would play an important role when we do the cross-validation or we do the optimization further. Okay. Okay. So mostly what will you do is you will be using the various algorithms using the cross-validation, and 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 then you will do the further optimization. Okay, you will do the further optimization based on what we are learning. All right, like the way we learned about regularization, the way we learned about various performance measures, and so on. Good. Great. Now using decision trees, we can also do the regression, not only the classification. Okay, so basically, though the idea of decision tree looks like very much for classifying things, but with decision trees, we could also do the regression. Okay, what is regression? In which we have to predict a particular value. Okay, so let's try to build a regression tree using scikit-learn's decision tree regression, and let's try it on the quadratic dataset. Okay, so we are saying decision tree regression. Let's just go back here. Okay, so this is our quadratic data. You can see we're importing NumPy, importing PLT, and here we are saying generate. We put a random seed. Then we are saying number of instances 200. Then we generate capital X. Then we generate Y, and this is the value of Y. We are also adding some amount of randomness to it. Okay. So then what we're doing is from the scikit-learn tree, sklearn.tree, we are importing decision tree regression. And decision tree regression, we are passing max depth and random state. Okay. So this is something that we have just now fit. So training, this is the model that is as in the various parameters of the model that have been chosen. And further, let's just try to plot this. Yeah, here we go. So this is how it looks. This is how it looks. Okay. So if there is a feature x1 and there's the y, see, y is what? Y is the actual value. Okay. So all right. This is how the decision tree looks like. See. All right. So if you want to say do a prediction for x1 equals to 0.6, okay, and basically for 0.6 it'll go this side, and then Okay, then yes, here. So the value will be 0.11. Okay. All right. So this is how we so let's just get into more details about regression. The main difference is that instead of predicting a class in each node, it predicts a value. Okay, it predicts a value. So notice that how the predicted value for each region is always the average target value. So here, when it decides when we are doing the regression using recent tree, this value that you see is the average value, is the average target. Okay, average target in this one, and so on. So it basically is picking up that particular value here while training that particular value here, which is closest to the instances. Okay, or which is dividing the instances such that the both sides are closest to the separator. Okay, so it is picking the that threshold, that particular threshold, such that both sides are closest to it. That's how it is generating the regression tree. Okay, so the cart algorithm works the same way in case of regression. Okay, works the same way, except that instead of trying to split the training set in a way that minimizes the impurity, it now tries to split the training set in a way to minimize the error. Okay, in a way to minimize the error. Okay, minimize the mean square error. And the mean square error is this. Okay, so the formula for regression is this. The So we have to split the data such that the mean square error on the left multiplied by total instances of left plus the mean square error on the right multiplied with the instances on the right, and that's how it is doing. So basically, this is the cost function for regression. So it is trying to draw the line in the data where this is minimum, where the mean square error is minimum. And how does it compute mean square error? Mean square error at every point is what is the average value of, okay, of y minus yi. Okay. Okay, let me try to do it again. Let me try to explain again. So what it does is at every point of time, it is going to draw a line, okay, and it'll compute the MSE on left as well as MSE on right. How does it compute MSE? What it will do is, first of all, given all the data point, it will compute the average. Let, okay, it will compute the average of all the values. Okay, so basically, can I just make it zoom it a bit more? Yeah. Here, what it is going to do is compute the average of all these data points, compute the average of all these data points, and then uh, so it'll basically uh, compute the weighted mean of the two, this average and this average, and minimize that, right? So imagine that we split the data here like this, and all right. So let me just go back here. Let's say we have split it here. Let's say instead of here, we are splitting it here. What will happen is the average will be somewhere here, correct? Therefore, the MSE will be higher on both the sides. Okay, MSE will be higher on both the sides. Let me explain again. So this is what it is going to do. So first of all, it'll at every point, whenever it draws the line, is going to compute the average value of all the data points. Once it has done that, after drawing the line, okay, so after drawing the line, it is going to subtract these, subtract it and square it. So how far each instance is from the average. Okay, now this average will be different because these average will be different. You might wonder that every time, whenever we split, the average is going to be same. No, average is going to be different every time because the total number of records are different. Okay, total number of records are different. So here, if we, let's say, divide it, instead of there, we divide it here. So on one side, we have 0 instance. On the other side, we have many. On the one side, we'll get the 0 average and so on. And on the other side, we will have the average, something as average, and then, okay. So basically, this function, this cost function, will ensure that the line we draw everywhere is kind of in the middle of the data. Okay, line we draw will be kind of in the middle of the data. So that's basically the regression. Okay, a question from Bintao: how to draw decision tree picture here? You can actually draw it using this piece of code. Okay. All right. In the Jupyter notebook, you will see, I think, 26th cell. All right. Okay. A question from Noor is, so it is always from the middle of the data set. How would it look for the linear regression? Good question. Good question. So let's say our data was, all right. Right. So basically, in case of linear regression, it'll basically try to split. Let's just think of this part alone, this part alone. So you can see that here also it is kind of trying to do the linear regression. I mean, kind of dividing this data and so on. So it's going to divide it into small pieces such that it is able to draw many lines. So it's kind of going to be staircase. Right? In case of linear regression, it's kind of going to be like a staircase. All right. Good question, Manur. Question from Binta: is the tree for a decision tree regressor looks something like this? Okay. This code, are you not able to see with this piece of code? Or you want me to explain it? Yeah. This one. Ah, okay. 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 Okay, actually you can draw it using the same mechanism that we have done in the beginning. You can just export the graph, okay, export it and then convert it. All right, say, where did it go? We were here, right? So the algorithm is tree regression 1, okay. So let's just try to do tree regression 1, okay. Okay. All right. So it says that the length of feature names 2 does not match the number of features 1. Okay. Feature name. Oh, we have to give the feature name ourselves. Okay. So it has done this. I've removed the feature name part. It should work, right? Yeah. Okay. I'll just, yeah. So we are saying iris dot. Is there iris dot anywhere? Yeah, sorry, this is tree-rag1. Okay, tree-rag1. I think using this you can generate this. Okay, let's just see if it did anything. Yeah. Is that your question, Binta? All right, great, great. So we were able to do this. Wonderful. We will continue from here, and we hope to learn tomorrow. We hope to complete the decision tree, and also we will start with ensemble. Okay, great set of questions, and I look forward to see you tomorrow. Sure, I'll commit it. Yeah. Thank you, everyone. Thank you, Noor.